When an industrial pipeline fails under high pressure, the resulting spray is a massive, continuous force. At this scale, the immediate physical danger zone is easy to identify. The conditions change during the catastrophic failure of a transportation vessel, like this overturned tanker truck. Here, the release of material is often violent and instantaneous, rather than a steady stream. Once the initial physical rupture ends, a dense, invisible cloud of toxic vapor begins rolling across the landscape. These vapors are often heavier than air, clinging to the ground as they move downwind. Predicting the path of this gas requires process safety engineers to calculate exact evacuation distances and perimeters before the cloud ever reaches a populated area. Within the standard consequence analysis flowchart, predicting the threat zone depends on the selection of a specific dispersion model. This selection is based on the properties of the chemical release, specifically whether the escaping material is flammable, acutely toxic, or both. Standard mass balance equations are insufficient here because atmospheric wind turbulence and eddy diffusivity fluctuate too wildly to measure. To manage this chaos, engineers use the Pascual-Gifford dispersion models. These rely on a Gaussian distribution to predict how the average concentration of the gas will spread downwind over time. This framework converts unpredictable weather variables into the rigid, actionable safety perimeters required to manage an industrial site. Calculating these perimeters begins with atmospheric stability, which dictates the degree of vertical mixing in the air above a release. Stability is determined by the environmental lapse rate, the actual drop in air temperature as altitude increases, relative to the theoretical adiabatic rate. In a state of absolute stability, a rising gas parcel cools faster than the surrounding environment, losing buoyancy and stopping at 2,000 meters. During daytime instability, the environment cools rapidly, driving continuous vertical motion that allows gas to mix aggressively through the 4,000-meter mark. At night, the ground cools rapidly, creating an inversion layer where temperature actually increases with height. This creates a physical ceiling that traps pollution plumes close to the ground. These behaviors are categorized into 6 Pascual-Gifford stability classes, ranging from A to F, which serve as the master scaling factor for the dispersion math. Engineers utilize the plume model to analyze continuous, steady-state chemical releases. This jagged line represents a chaotic, instantaneous plume, impossible to predict with a single equation. However, averaging this motion over a 1-hour period produces a smooth bell curve. This concentration profile allows us to predict the average gas density at any point downwind. This bell curve is mapped onto a 3D coordinate system, traveling from an elevated point source along the wind direction. As gas moves further down the x-axis, the curve flattens out. The plume spreads wider, but peak toxic concentration decreases. This geometric spread is dictated by dispersion coefficients, which represent the standard deviations of the cloud in the vertical and crosswind directions. These coefficients are extracted from logarithmic charts corresponding to different weather conditions. To find the coefficient, locate the downwind distance on the x-axis, move up to the current stability class line, and read across to the y-axis to find the value for sigma y or sigma z. The point of origin is rarely the ground itself. The momentum of a high-velocity jet or the buoyancy of hot gas pushes the material higher, creating an effective release height. Because of this elevation, the plume must travel a significant distance downwind to disperse vertically before it ever reaches personnel on the ground. Increasing this effective release height is a primary strategy used to reduce the immediate threat of toxic exposure at the site of the failure. When a vessel ruptures instantaneously, it does not create a steady plume. Instead, it releases its entire inventory as an isolated puff. Analyzing a puff requires a coordinate system moving alongside the cloud center at wind speed. Because a puff disperses outward in all horizontal directions simultaneously, the model assumes the downwind dispersion coefficient, sigma x, equals the crosswind coefficient, sigma y. These dynamics require a different set of empirical charts, shown here with the sigma x equals sigma y notation on the vertical axis. The puff model defines a moving, highly concentrated mass of toxic gas, requiring emergency responders to track the hazard as it travels through a community. These variables combine to find the ground centerline concentration. In this specific equation for ground-level releases, the release height is set to 0. For releases at ground level, the absolute maximum concentration is found precisely at the point where the rupture occurred. For elevated releases, engineers use optimization calculus to find the vertical dispersion coefficient, which identifies the exact downwind distance where the ground concentration will peak. This downwind coordinate defines the worst-case exposure zone and dictates where it is safe to establish emergency command posts. Calculating peak concentration alone does not fully measure the impact of a puff because the cloud is in constant motion. To find the true human impact, we calculate the integrated dose, the time integral of the concentration as the puff passes over a stationary person. Exposure levels depend on weather stability. High winds and unstable air disperse the cloud quickly, reducing the total dose received at any one location. By applying Pascual-Gifford dispersion models to industrial failures, safety engineers can establish the precise mathematical parameters that save lives during a crisis.